Hey folks, in lesson 25 we're going to deal with the angular momentum separation. And this is going to give us some useful tools for solving these dynamic systems with multiple particles. But also, this is a great stepping stone into moving into rigid body mechanics. So in lesson 24, we developed an expression for the total angular momentum of a system of particles. Now, recall that we pointed out that this doesn't have a pure analogy with the total linear momentum of the system of particles, because we can't simply say that the total angular momentum about an inertially fixed point is equivalent to the total angular momentum about the center of mass. We want to use the center of mass to our advantage, but this expression isn't true in the same way that the total linear momentum of the center of mass is equal to the total linear momentum of the linear momentum of the center of mass is equal to the total linear momentum. But we can use this center of mass to our advantage. And so let's work out the expression so we can take this into consideration. So if we start with our expression for our total angular momentum, then we see that to get the total angular momentum, we're simply adding up the angular momentum of each individual particle about an inertially fixed point, and here we call it the fixed point O. Now if we reference each particle to the center of mass, then there's a position vector of r of I with respect to g, and then of course the center of mass itself has its own position vector of r of g with respect to O. So let's substitute in this, let's take this expression. So for each particle, I with respect to O is equal to the position vector of the center of mass with respect to our inertially fixed point plus the position of the particle with respect to the center of mass. And let's take this expression and substitute this into our expression for total angular momentum. And so when you substitute this in, we're going to get that the total angular momentum is equal to the sum of all the particles from I is equal to 1 to n of our mass of each particle, and then it's r of g with respect to O plus r of I with respect to g crossed with the velocity of g with respect to O plus the velocity of I with respect to g. Now when you get these somewhat ugly expressions like this, the best thing to do is just expand your cross products and then deal with each term individually. So let's do that. Our cross product for our total angular momentum is going to be equal to the summation from 1 to n of r of g with respect to O crossed with the masses multiplied times the velocity of g with respect to O plus r with the center of mass with respect to O crossed with all the masses multiplied times the velocity of I with respect to the g. And then our last two terms plus r of I with respect to g, so the position vector of I with respect to the center of mass, cross with the mass multiplied times the velocity of the center of mass with respect to O, plus one more term, which is r of I with respect to the center of mass, position vector of each particle with respect to center of mass, cross with the mass multiplied times the velocity with respect to the center of mass. So let's deal with each of these terms individually. So for this first term, we see that we have the position vector of the center of mass with respect to the inertially fixed point, the velocity of the center of mass with respect to the inertially fixed point, and then we have the summation of all the masses. So there's not much we can do with this first term, except for we can substitute the summation of all of our masses with mg. And so that's a helpful simplifying expression if we know the total mass of the system. Now let's look closely at the second term, and we see that we have the position of the center of mass with respect to inertially fixed point cross with the summation of all the masses multiplied times the velocity of each mass with respect to the center of mass. So let's take this last expression, which says the summation of all the masses multiplied times the velocity with respect to the center of mass of each mass. Now we can rewrite this as the summation of each mass multiplied times the time derivative of the position vector of r, I with respect to g. And remember, we've got some flexibility in what we do with our summations, and so if we move this inside of our time derivative, then we get the time derivative of the summation of mi ri with respect to g. And so you should recognize here that this summation of the masses multiplied times this position vector, which is related to the center of mass, is our center of mass corollary. And what we said is that this term is equal to 0, because that's a balance of all the masses about the center of mass, and that balance is going to be 0. And so this means we can take this entire term and set that equal to 0, and it actually is 0. Okay, so moving on to our third term, we have our position vector of each mass with respect to the center of mass crossed with the summation of all the masses multiplied times the velocity of the center of mass with respect to the inertially fixed point. And so we can move our mass anywhere in these expressions, and we get our summation of mi ri with respect to g crossed with our velocity of center of mass with respect to o. And this is also our center of mass corollary, and so this expression is 0, and because that's 0, that means this term goes to 0. All right, let's move to our fourth term, and we see that we have the summation of our position vector of r, or our position vector of each particle with respect to the center of mass, crossed with the mass times the velocity of the particular particle with respect to the center of mass. And so this has to stay the same. There's just not much we can do with this term in terms of simplifying it. But you can see here that what we've done is we've eliminated, by considering where the center of mass is, and by making this substitution of each particle relative to the center of mass, we've done our cross product and we've eliminated 2 of the terms. And so we're left now with the expression for the total angular momentum of the position vector of the center of mass with respect to an inertially fixed point crossed with the mass of the entire system multiplied times the velocity of the center of mass with respect to an inertially fixed point. All this observed in an inertial reference frame. And then our fourth term we keep, which is our summation from 1 to n, this is across all the particles, of the position vector of each particle with respect to the center of mass crossed with the individual mass multiplied times the velocity of the individual mass with respect to the center of mass, as observed in the inertial reference frame. And it's these 2 expressions that we condense our notation now into our total angular momentum is equal to the angular momentum of our center of mass as observed or with respect to an inertially fixed point, plus our angular momentum of the entire system, so of each particle summed up about the center of mass. And so now our total angular momentum is completely separated into 2 independent angular momenta. Like we said, one which is the center of mass about an inertially fixed point, and then the second angular momentum, which is the momentum of the entire system about the center of mass. And so if you can find both of these, h of g with respect to O and then h of g, we can simply add them up to get the total angular momentum. And so we also see here that this completes our observation that our total angular momentum is not equivalent to the angular momentum about the center of mass. Instead, we need this term here that gives us that separates the two, but then gives the correct expression. Now, as you know, momentum and angular momentum is a great way to describe the motion of the system. But the usefulness of these terms come when we take the time derivative of momentum, and then we get the dynamics of the system. Now here we're going to see that the dynamics themselves also separate. And so if we take the time derivative of the total angular momentum, this is simply applying the time derivative of the total angular, or the time derivative of each term within the angular momentum. Of course, everything here, time derivative as observed in the inertial reference frame. And if we look at the first term, then the time derivative of our angular momentum of the center of mass with respect to an inertially fixed point, then this is equal to the time derivative as observed in an inertial reference frame of rg with respect to O crossed with mg of the velocity of g with respect to O as observed in the inertial reference frame. And so we apply the chain rule to this, so we get the velocity of g with respect to O as observed in the inertial reference frame crossed with the mass of the entire system multiplied times the velocity of g with respect to O as observed in the inertial reference frame plus r of g with respect to O, our position vector, crossed with the mass of the entire system, and then the time derivative of this term is the acceleration of g with respect to O. Alright, we know quickly that the velocity vector crossed with itself is equal to 0, so this first expression goes to 0. And then also, our term here, which is the mass of the entire system multiplied times the acceleration of g with respect to O. We know from the previous chapter that this is equal to all the forces, all the external forces onto the system. And this arises, of course, from our equating the total linear momentum to the linear momentum of the center of mass. And so our expression for the time derivative as observed in the inertial reference frame of the angular momentum of g with respect to an inertially fixed point is equal to r g with respect to O crossed with Fg of only external forces, and then this is equal to the moment, because we have r cross F, the moment of g with respect to O that's only due to external forces. So once again, we find that we can solve for the motion of the center of mass, the dynamics of the center of mass, without considering the internal forces or the movement of the external forces. All we need here is the moment of the center of mass about point O, the moment of the center of mass about point O due only to external forces, and that's equal to the time derivative of the angular momentum of the center of mass about our inertially fixed point O. So now let's take a look at the second term in this expression, which is the time derivative of the angular momentum of the system about the center of mass. Now recall that we separated this out, and so we can write this as the time derivative as observed in the inertial reference frame of this expression, where we're now summing across all of our particles. So the position vector of each particle with respect to the center of mass crossed with the mass itself multiplied times the velocity with respect to the center of mass. And here, we're not going to work through every single step of this derivation, but just suffice to say that with judicious use of our center of mass corollary, which says the sum of all the masses multiplied times the position vector of each mass with respect to the center of mass is equal to 0, with judicious use of this center of mass corollary. And then, this is important, we're assuming no internal moments. Internal moments. So when we apply this condition, assuming no internal moments, we end up with the expression, which is really convenient. That's the time derivative of the angular momentum of the system about the center of mass is equal to, it's going to be the summation of the position vector of each particle crossed with only the external forces on each particle and then we end up with the expression that this is R cross F, which is a moment, but it's going to be all the moments on each part. So it's the moment on each particle due to each external force acting on that particle. And so then we simplify that notation as saying it's the moment about our center of mass due only to external forces. And so the final expression here is the time derivative as observed in the inertial reference frame of the angular momentum about the center of mass is equal to the moments about the center of mass only due to external forces. And so what we get here is that the dynamics, so we started out by saying that the angular momentum separates completely into two terms, and then we take the time derivative of each of those terms, and then from this we see that the dynamics themselves of each term separate still. And we get from this two equations of motion that we can use. The first equation of motion to be able to solve for the motion of the center of mass with respect to an inertially fixed point, and then the second is an equation of motion in which we're solving for the movement of the entire system, the motion of the entire system, and this is about the center of mass. So a couple things to point out about our two equations of motion now is that neither of these are based on translational motion of the center of mass at all. So that's an independent entity, and we're only looking at this rotational motion in the first about the center of about an inertially fixed point, and here this isn't based on the rotational motion about an inertially fixed point at all. And so we see that when we're trying to, if we're applying conservation of angular momentum, then this first term can be conserved independently of the total angular momentum because of the angular momentum separation. Now, this is interesting but not terribly useful. The most interesting point is in the second term, because this tells us, and to quote the book, that even if there are external forces acting on the system that result in acceleration of the center of mass, this is going to affect this first term. So even if this term exists where we have moments of g with respect to O due to external forces, and even if they result, we're saying even if they result in a moment about an inertially fixed point O, we can still conserve the angular momentum of the system about the center of mass as long as the moment about the center of mass due to external forces is equal to 0. Alright, this is expressed a little bit more succinctly in this sentence that says, if the total external moment acting on a system of particles about the center of mass, g, is 0, then the total inertial angular momentum about the center of mass is a constant of the motion. Now this is a huge result because it allows us to separate the translation of the center of mass, which we learned about in the last chapter, when we're talking about the total linear momentum is equivalent to the linear momentum of the center of mass, and we can separate that from the rotation of the rotation of the system about the center of mass. And so this gives us two very powerful equations to use. We say that the time derivative, as observed in the inertial reference frame, of the momentum, so this is the linear momentum of the center of mass with respect to an inertially fixed point, is equal to the sum of all the external forces on the system. And then we also now developed a new expression, which is the time derivative of the angular momentum of the system about the center of mass, as observed in the inertial reference frame, is equal to the sum of all the moments about the center of mass due only to external forces onto our system of particles. And so we use these two properties to solve dynamic systems of multiple particles, and then we can move this now. This gives us the foundation to move into rigid bodies, which are systems of multiple particles which have fixed orientation with respect to each other. So let's apply this now to the example that we saw in the book, which is to these tethered satellites. So we've got a pair of tethered satellites that have identical mass, m, and they each have a thruster which operates a force which can apply a force perpendicular to this tether that's between them. And then if they fire, so if they start from rest and they fire with an identical force and identical duration to essentially create that rotational motion about the center of mass, then we want to, with this problem, determine the maximum duration, the maximum time that both thrusters can fire, to obtain a centripetal acceleration on P and Q that's less than 2 Gs. So to do this, they need to fire in equal and opposite directions to create that rotational motion. And so we're saying that the force by Q is equal to the negative force by P. And so we see that the absolute value of these, the magnitude rather, of these are the same, and we'll just call that F. And to get the equation of motion of the system, we're going to take the time derivative of the angular momentum about the center of mass, and we're going to set that equal to the sum of all of our moments due to external forces. And so these are our external forces, the force due to each of these thrusters. So we set up our reference frames. We need to have an inertial reference frame which is given to us, which the inertial reference frame has a fixed point O, and then we have EX, which is along PQ when theta is equal to 0. EZ is coming out of the plane of motion, and then EY is equal to E sub Z crossed with E sub X. And we apply a second reference frame to this problem, B, which has an origin at the center of mass, and then B1, B2, and B3. B1 along PQ, and then B3, which is equivalent to the out of plane motion EZ, and then B2 is equal to B3 crossed with B1. And then the relationship between the reference frames, omega B, as observed by the inertial reference frame, is equal to theta dot in the B3 direction. Now we're solving for the centripetal acceleration of this system. So let's develop an expression for the centripetal acceleration. So for our kinematics, R of P with respect to our center of mass is equal to, in the B basis, it's negative L in the B1 direction. Our velocity of P with respect to G is equal to the time derivative of negative L B1. So this is negative L times the time derivative of B1. And so the time derivative of B1 is equal to omega B, as observed in the inertial reference frame, crossed with B1. And so it's theta dot B3 crossed with B1. And so we get theta dot b2. And then when we insert this into our expression, the velocity of p with respect to g is equal to negative L theta dot in the b2 direction. And we need to get our acceleration. So our acceleration of p with respect to g is equal to the time derivative as observed in the inertial reference frame of negative L theta dot b2. And this is equal to, using our chain rule, so we get negative L theta double dot in the b2 direction minus L theta dot multiplied times the time derivative of b2. So let's do that calculation off on the side. So the time derivative of b2 is equal to omega b observed in the inertial reference frame crossed with b2. And so that's theta dot b3 crossed with b2. And with that we get negative theta dot b1. And insert this back into our expression. So then the acceleration of p with respect to g, as observed in the inertial reference frame, is equal to negative L theta double dot in the b2 direction, and plus L theta dot squared in the b1 direction. Now we're only interested in our centripetal acceleration, which is this term. So we see that acceleration p with respect to g as observed in the inertial reference frame. And because we only want our centripetal acceleration, we can take the dot product in the b1 direction, and then this gives us our L theta dot squared. So here is our expression for our centripetal acceleration. It's this that needs to be less than 2g. So to obtain this, we need to solve for our equations of motion for the system, and then solve for theta dot. So our equation of motion we get by taking the time derivative in the inertial reference frame of the angular momentum of the entire system about the center of mass, and that's equal to the sum of all the moments due to external forces. And so we work with the left-hand side first, solve for each of these expressions, solve for our angular momentum, take the time derivative, then we have the entire left-hand side, and then solve for the moments due to external forces about the center of mass. So for the left-hand side, the angular momentum about the center of mass of the system is equal to the sum of the angular momentum of each of these particles, particle P and particle Q, about the center of mass. So we find the angular momentum of each of those and then add them up. So it's the angular momentum of P, or it's the angular momentum of P, which is the position of P with respect to G, cross with m multiplied times the velocity of P with respect to G as observed in the inertial reference frame, plus the position of Q with respect to G, cross with the mass multiplied times the velocity of Q with respect to G. And so we have the angular momentum of each mass itself about the center of mass of the entire system. And so we already know these expressions that go into the angular momentum of P with respect to the center of mass. And so we know that R of P with respect to G is equal to negative L in the B1 direction. The velocity of P with respect to G, as observed in the inertial reference frame, is equal to negative L theta dot in the B2 direction. So let's write these out for point Q. So it's the position of Q with respect to G, and that's equal to L in the B1 direction. And then the velocity of Q with respect to G, as observed in the inertial reference frame, is equal to the time derivative in the inertial reference frame of L B1, and this is equal to L multiplied times the time derivative of B1. Know that the time derivative of B1 is equal to theta dot B2. And so we substitute this in, get theta dot in the B2 direction. So let's insert this into our expression for our angular momentum of the system about the center of mass, and we get negative L B1 crossed with the mass multiplied times negative L theta dot B2 plus L in the B1 direction crossed with the mass multiplied times L theta dot in the B2 direction. So let's take our cross products. And we see that negative L multiplied times negative L is positive L theta dot, or rather positive L squared dot. And so we get M L squared theta dot. B1 cross B2 is in the B3 direction. And then for our second expression, it's L squared theta dot. So M L squared theta dot. And then B1 cross B2 is in the B3 direction. And so our final expression for our angular momentum about the center of mass is 2m L squared theta dot, and that's in the B3 direction. So always pause for a moment and take a look at your system, and does it make sense? And if we've got our thrusters firing in equal and opposite directions to create a rotation, what we see is a counterclockwise rotation, then the angular momentum of this system, as the thrusters are firing, should be equal to, if they're firing in a positive direction, should be in the B3 direction, which we get in our expression. And because they're equal and opposite, we should have the same term added to each other. So next, let's take the time derivative. To finish off the left-hand side, take the time derivative of the angular momentum about the center of mass. And the only differentiable element that we have in this equation is theta dot. So the time derivative is 2ml squared theta double dot in the B3 direction. All right, let's take a look at our right-hand side. The right-hand side, we need to calculate the moment about G due to only external forces. And so our free body diagram of the system, where we have P, we have Q, then there's our point G, and because they're equal masses, it's the same length in between them. And then we have our force F in the B2 direction, and then we have a force on P, which is in the negative, so it's the magnitude F in the negative B2 direction. And that completes our free body diagram. So the total force on the system is equal to 0, and so our moment, which is what we need for this expression, are two cross products, R of P with respect to G, cross with the force on P, and then plus R of Q with respect to G, cross with the force on Q. So the moment that we're solving for is equal to the position vector of P with respect to G, which is negative L in the B1 direction, and this is crossed with negative F in the B2 direction, then plus L in the B1 direction crossed with F in the B2 direction. This is equal to FL in the B3 direction plus FL in the B3 direction, which should make sense. We've got a pure couple that's happening, so the moments add up. and so this is 2FL in the B3 direction. Let's equate our left-hand side and our right-hand side. So for our left-hand side, we've got 2ml squared theta double dot, and that's equal to 2FL. And solving for our equation of motion, we get theta double dot is equal to F over m times L. Let's solve our equation of motion for theta dot so we can use this in our expression for centripetal acceleration. And so if we have theta double dot is equal to F over m times L, then we're going to integrate both sides, okay, with respect to time. And then from this we get theta dot is equal to F over m times L multiplied times t, because that's a constant. Force is a constant, mass is a constant, length is a constant. And then this will be plus theta dot at time 0. The system starts at rest, we said, so that's equal to 0. And so we plug this into our expression that we're solving for, which is L theta dot squared is less than 2g. And so we want to solve for the time, and recall the problem, we want to solve for the time that these thrusters can apply a force that can still keep the centripetal acceleration of less than 2g. And so when we insert theta dot into our expression, we get L F over ml times t, the entire quantity squared, is less than 2g. And for this to happen, our time needs to be less than the square root of 2g over L multiplied times ml over F. And then our final expression is that our time is less than m over F multiplied times the square root of 2gl. And so we see that our solution here to create this essentially artificial gravity in space, we see that the time in which these thrusters would fire is inversely proportional. It's proportional to the mass, but is inversely proportional to the force that's generated by the thrusters. And then it's scaled by this coefficient here, which is 2gl, which is relating our condition, which we said we don't want to exceed 2g, to the length of the tether. The length of the tether, the length or the distance between each particle between the center of mass, which is dictated by the length of the tethers. So this is a very useful form. What we've done is we've separated our angular momentum, and now we've worked with the dynamics only of the system of particles about the center of mass, completely separately from our total angular momentum. We can use this conservation law, we can use this equation of motion independently of anything else. And you'll find that when solving dynamics problems, starting with the center of mass and applying this equation of motion, this approach for the equation of motion is typically the most efficient way to get a scalar equation of motion that you can then solve for your problems. Alright, that does it, and I'll see you in class.